Hi everyone, welcome to this section on Gaussian mixture model clustering, also known as GMM clustering. So this is the fourth clustering technique which we are going to learn in our course. This is different from the previous three clustering technique because this is also known as soft clustering technique, whereas the previous three clustering techniques were hard clustering techniques. So what we are going to cover in this section? So in this section, these are the topics which we will cover. First, we start with the definition of GMM clustering. In this definition, we will see why it is also known as soft clustering and how it is different from the hard clustering techniques. Then we will discuss the limitations and the shortcomings of k-means clustering. Since k-means clustering is a hard clustering technique, therefore it has some limitations or the shortcomings. We will also see how GMM clustering will address those limitations. Then we will solve three projects on GMM clustering. Then we will learn binomial distribution. We will learn binomial distribution because it is the important part of expectation maximization algorithm. Expectation maximization algorithm is the algorithm which is used in GMM clustering to update the value of the mean and variance of the clustering. So these are the important topics which we are going to cover in this section. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will learn the basic concept and definition of Gaussian mixture model clustering, or in short, GMM clustering. So here is the definition of GMM clustering. So this is the clustering which assumes that data comes from certain number of Gaussian distributions, and each of these distributions can form a cluster. Thus, GMM clustering tends to group together the data samples belonging to a single distribution. So we see from this definition, the basic concept behind GMM clustering is the data is coming from different Gaussian distribution. Suppose we have three different Gaussian distributions and data is coming from those, it means GMM clustering will group the data into three clusters. So if data is from five different Gaussian distribution, in that case, GMM clustering will group the data into five cluster. So what is the basic concept of Gaussian distribution? How Gaussian distribution looks like? So this is the basic of Gaussian distribution. This is the basic shape of a Gaussian distribution. We can see that it is very nice symmetrical bell-shaped curve, and we have drawn this curve from this equation. So this is the equation of Gaussian distribution, where mu is the mean of the distribution and sigma square is the variance of the distribution. If we take a square root of this variance, we will get the sigma, which is the standard deviation of the Gaussian distribution. So standard deviation of the Gaussian distribution will tell us about the spread of the Gaussian distribution along the mean line. So this is our mean, and for this particular Gaussian distribution, the mean is 0. So this is the Gaussian distribution, which is the basic assumption for GMM clustering. And if we have more than one Gaussian distribution, it means their mean will be different and their variances or standard deviation will be different. Here is the example of three different Gaussian distributions, and we can see that for all these three Gaussian distributions, the mean is different, the spread is different. So according to GMM clustering, if data comes from these three different Gaussian distribution, then GMM will group the data into three clusters. So that is the basic definition and basic concept behind GMM clustering. So I hope you understood the definition of GMM clustering. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will discuss the limitations of k-means clustering, and we will also discuss how GMM clustering will address those limitations. So k-mean clustering uses the mean to update the centroid, while GMM uses means and variance of the data. So the first difference is that in k-mean, there is a centroid, and we need to update the centroid after every iteration by using the distance of the data samples, while GMM using mean and variance of the data. So basically in k-means, we update the centroid, while in GMM, we update the mean and variances of the Gaussian distribution from which the data comes. The other is k-mean is the hard clustering, whereas GMM clustering is soft. Now, what does it mean, hard clustering and soft clustering? So k-mean tells us which data sample belongs to which cluster, but unable to tell the probabilities of the membership of a given data sample with the cluster. Now, k-mean is the hard clustering. GMM is the soft clustering. Now, what happens is that if a data point is at the overlapping of the two cluster, k-means will not tell us anything about that data point, and it will assign only one cluster to that data point. Now, what GMM clustering will solve this problem, and how GMM clustering will solve this problem? GMM clustering will assign the probability to that kind of a data sample which is at the border of two cluster. And GMM clustering will tell us that it is a 60% probability that this data point belongs to cluster 1, and there is a 40% probability that this data point belongs to cluster 2. In this way, GMM clustering is called a soft clustering or a membership clustering. It assigns a membership in terms of probability to the data points which are present, especially at the border of more than one cluster. On the other hand, K-means cannot provide that kind of membership. That's why it is known as hard clustering. Now, why K-means is a hard clustering? So the problem is that K-means has a centroid. Now, centroid has to be located at the center of a cluster. Therefore, most of the time, the shape of the clusters of K-means is either circular or some symmetric shape, so that centroid should reside at the center of that cluster. On the other hand, there is no such limitation or restriction with the GMM clustering, and GMM clustering can take any shape according to the mean and variance of a distribution, because there is no centroid in the GMM clustering. Let's see another example. Now, here is the example of k-mean clustering having 5 clusters. Now, we can see that these clusters looks like independent, but they are not very well separated. Now, if you see this light blue point and this red point, they are very close to each other. Now, there is a chance that this red point may be at equal distance to this centroid and this centroid. So there is a chance that this red point is at the midpoint of these two centroids. But k-means clustering will not address this issue, and it will assign this point to this red cluster. The same can be happen with any point. So that is the limitation of k-means clustering, that it assigns a one cluster to a single data point. That's why it is a hard clustering. Now, this problem is more obvious if we draw the shape of the cluster around the centroid. If you see, these two centroids or these two clusters are very large. That is the cluster 5 and cluster 2. These clusters are very large. The reason is that there is a point in both these clusters. There are the points which are far away from the centroid. So in order to accommodate this point, this cluster has to spread symmetrically on both sides of the centroid. In that case, what is happening, that we do not have any point at this part of the cluster, and we do not have any point at this part of the cluster. Similarly, these two clusters are spread so far around their centroid that they are overlapping, rather passing through the other cluster. Now we can see that if we consider this blue point, now this blue point is at the border of 3 clusters: this big cluster, this small cluster, and this small cluster. So this light blue color has a membership of 3 clusters. So the k-mean clustering will not address this problem, and it is assigning this blue point to this cluster. So the k-mean cluster is a hard cluster, or k-means clustering is a hard clustering, because it assigns only one cluster to a one data point, and it does not address the problem if the data sample is present at the border of the cluster or between two clusters. So you can see that this figure clearly illustrates the problem of a k-mean clustering. Now, if you compare now both these figures, this is k-mean clustering without drawing the shape of a cluster, and this is k-mean clustering with drawing the shape of the cluster. So the shape of a cluster in k-mean clustering is symmetric, because the centroid should be present at the center of a cluster. Now, from this figure, where we do not draw the shape of the cluster, we cannot see the limitations of the k-mean clustering. Here we can clearly see the limitation of a k-mean clustering, and we can clearly see that there are many points or many data samples in this data set which has the membership of more than one cluster. So how GMM clustering will address this problem and why GMM clustering is called soft clustering or a membership clustering. So now look at this point. Look at this brown point, which is of large size. Now this point is at the border of 3 clusters. So that's why it has a triple membership. So this is a triple membership point. What will happen when we will implement GMM clustering? The GMM clustering will assign 3 probability values to this point. So GMM clustering will say that this point has 60% membership with this cluster, maybe 30% membership with this cluster, and 10% membership with this cluster. So this triple point membership will be assigned by the GMM clustering only. That's why GMM clustering is also known as soft clustering. So in this lecture, we see that K-means clustering is a hard clustering technique and GMM clustering is a soft clustering technique. K-means clustering cannot address the problem for those points which are present at the border of more than one clusters. However, GMM clustering will assign the memberships in terms of probability to those points so that a single point may have the membership of more than one cluster. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will implement Gaussian mixture model in Python. So this is our project 1 of GMM clustering. So here I am at my Google Drive. This is my course folder. Click on the folder. So inside my course folder, I have 3 major sections. And here is unsupervised machine learning. Click on this folder. And we have Gaussian mixture model. Click on this folder. So we can see that we have a project 1 here. If I click on this file, it will be open in Google Colab. So click on this file so that it can be open in Google Colab. So here, this is a file in Google Colab environment. Now, what we are going to do in this project, basically, we will learn how to implement GMM clustering in Python. Then we will see the limitations of K-means clustering. We will also see how GMM clustering will address those limitations. So these are some things which we are going to learn in this project 1. So the first step is that I have to import all the necessary Python libraries. So these libraries are NumPy, Matplotlib, and Pandas. Let's run this cell to import all these libraries. Now, for this project, I have to use a dataset known as mol_customer dataset. Now, this dataset is present inside my folder. And we know that if we want to read the dataset in our Google Colab environment, which is present in our folder, we have to mount the drive and we need to set the path. So in order to save the time for this lecture, I have already mounted the drive. You can see here, the drive has been mounted, and I have here the drive has been mounted, and I have also set the path. So this is the path of the dataset. That is, the dataset is inside the folder drive, my drive. Then inside my drive, we have course material, unsupervised machine learning, and Gaussian mixture model clustering. So this is the path of our dataset. Since path has been set, now we can successfully read the data. Let's run this cell to read the data. Now this is the dataset which you have seen more than one time in this course. You have seen this data in the section of hierarchical clustering and also in the section of K-means clustering. Now this dataset has 5 columns or 5 features. These features are customer ID, the gender of the customers, age of the customers, annual income, and spending score, which ranges from 1 to 100. Since we have to plot the cluster and we have to visualize the cluster, we will select only 2 important features, that are annual income and spending score. So here I am extracting those 2 important features which are at the column 5 and column 4 of the dataset. Let's run this cell so that we can extract the feature. So we can see that we have not only extracted the features, but we have extracted the features in terms of NumPy array. Now, first we will get the K-means clustering. In order to compare GMM clustering with K-means clustering, first we will plot K-means cluster. And we know the very important step of plotting K-means clustering is first to get the elbow method first to get the elbow plot so that we can find the optimal number of cluster. So the first step now is that we will use elbow method to find the optimal number of cluster for k-means clustering. Now this is the same code of elbow method or to generate elbow curve, which you have seen many times in the section of k-mean clustering. So here I am generating it for 10 cluster, and out of these 10 cluster, I will select the optimal number of cluster. Let's run this cell and see the elbow curve. So this is the elbow curve for this particular data set, and we can see that here the number of clusters are 5. So if we divide the curve at this point, we can see that before this point, there is a significant change in within cluster sum of square. And after this point, this change is almost flat and it is not very significant. So we have decided to select 5 cluster for this data set. Now plot the cluster for k-means for this data set. So first we will apply k-means clustering. We have decided that we will have 5 cluster. So this code is also exactly the same code which we have seen in the section of k-means clustering. Let's run this cell to get the predictions. Let's see the predictions here. Now we can see that according to these predictions, we have 5 cluster, and our first data sample belongs to cluster 3, and our last data sample belongs to last cluster, which is the 5th cluster. Now here I am getting the centers of the cluster, and here I am plotting the clusters so that I can visualize the cluster and I can see the limitations of the k-means clustering. Let's run this cell. So we can see that these are our 5 clusters, and we can clearly see what we have learned in the previous lecture, that there are many points in this data set which belongs to more than one cluster. Now, if we can see that here there are many red points which belongs to this cluster, which is the cluster of red point, and this cluster, which is the cluster of magenta points. And there is a point of a light blue color which is present at the border of 3 clusters. But the problem is the k-means clustering does not tell us this problem. K-means clustering does only assign one cluster to each data sample. So that is the limitation of a k-mean clustering. K-mean clustering is unable to give the membership of a data point with more than one cluster. Now, how GMM clustering will address this problem? Now we are going to applying Gaussian mixture model clustering. First of all, I am importing a Gaussian mixture from sklearn.mixture. Here I am instantiating the Gaussian mixture with number of components is equals to 5. Because we have 5 cluster, so we are passing number of components is equals to 5 in Gaussian mixture model. And here I am fitting and I am getting the predictions. Let's run this cell to get the prediction for GMM clustering. Here is the prediction of GMM clustering. If we see that we have 5 clusters. Now, what is the difference between this prediction and the prediction which we obtained from k-mean clustering? If we see that GMM clustering assign cluster 4 to the first sample and cluster 3 to the last sample. On the other hand, the k-means clustering assign cluster 3 to the first and cluster 5 to the last sample. Similarly, there are many data samples which are assigned different cluster by GMM clustering as compared to k-means clustering. And the reason is obvious, that GMM clustering is based on the Gaussian distribution and it assigns the cluster based on the mean and variance of the distribution. On the other hand, k-means clustering is a hard clustering technique which assigns the cluster based on the distance of a data points from the centroid of the cluster. Now here we are going to plot Gaussian mixture model. We are going to plot the cluster of a Gaussian mixture model. Let's see. The code is same. This code is same. Only difference is that now I am using the prediction from Gaussian mixture model. Rest of the code is same. Now this is GMM clustering and we can see that there is no centroid here. Now if we compare this clustering with the k-mean clustering, now what is the difference? If we see, this is the location of the cluster 4. This is a cluster 4 of a light blue color. If we want to see this cluster in k-mean, its location is different. So basically, the first difference is that GMM clustering and k-means clustering are assigning a different cluster to same data point based upon their functionality. Now, where is the problem solved? How GMM clustering solve the problem of k-means clustering, which is a hard clustering? So the advantage with GMM clustering is that we can find the probabilities. So the command is gmm dot predict underscore probability of x. And if I run this cell, I can get the probabilities. So these are the probabilities. So if we see these probabilities, so every row has 5 values. Every row has 5 values. It means that these are the probabilities of 5 cluster. If I want to see the shape of this probability, then the shape of this probability is 200 by 5. Why 200 by 5? Because we have 200 data samples and we are dividing those data samples into 5 clusters. And this probability is assigning the probability to each data point with respect to the cluster. Let's understand this probability further. So these are the value of the probability. If we see the first data sample, according to this probability, the first data sample has the probability of 0.001 that it is present in the cluster 1. It has 0 probability that it is in cluster 2. Then 0 probability it is in cluster 3. And we can see that it has 99.9% probability or 0.99 probability that it belongs to cluster 4. So according to these assigned values of the probabilities, we are sure that our first data sample belongs to cluster 4. Let's check this. So here we can see that our first data sample has assigned the value 3, which is the value of cluster 4. Because index in Python start from 0, it means 3 means the cluster number is 4. So let's move on and observe these probability values more. Now there are many points. If you see this point, it has a membership with 4 clusters. That is the cluster 1, cluster 2, cluster 3, and cluster 4. But the difference is that it has 99% membership with cluster 1 and its membership with other cluster is very, very small. So let's find out the point which has some strong membership with more than one cluster. So if we keep on moving down, we might be able to get a point which has a cluster or membership with more than one cluster. So we have to find the point. Let's see where this point is present. So if we see here, this is a 94% probability of being with cluster 1. Here is a 93% probability. Now here is 15.7 probability, 82.2 probability of being with cluster 2, and around 0.7% of being with cluster 3. So we are looking for a point which has some strong value with more than one cluster. And that is maybe 70% or 80% probability with one cluster and maybe 10 to 20% probability with the other cluster. So we are unable to find that point. And it means let's find this point. So this has only 0.1% probability. Now this might be our point. Let find this point where this point is present in our cluster. So it has 15.7% chance with cluster 1, 82.2% chance with cluster 2, 0.7% with cluster 3, and 1.4% with cluster 4. So this point has a membership of more than one cluster. So let's find this point. How to find this point? So its first probability value is 0.157. So what we will do, we will use a command np where probability is equals to, now I have to check, the probability is 0.157. So if I replace this value by 0.157, so what will happen? If I run this cell, I will get the index of this data point. That is, we have 200 sample, I will get the index of this data point. And here I am finding this data point by passing this index to our sample. So this is XP point. Now I am plotting this point on top of all my cluster. Excuse me. Let's run this cell. And we can see that this point is present here. Now this point has, according to our values, this point has the probability of 4 cluster, but we can see that it has the membership of a 3 cluster. That's why it is called as triple membership point. So we see that the GMM clustering has solved the problem. Now we have put the probability and we were able to find the index of that point. Then we find that point, and here we are plotting this point with a brown color. And the size of the point, we have made it large so that it can be clearly visible. Similarly, student, you can find any point and its location in the curve. Suppose I want to find this point. Like this point we have already found, and I want to find this point if this is present somewhere. So the first value of its probability is 0.008. We might get a point in cluster 1 with the high probability. Let's put this value 0.008 in the equation below so that we can find its position. So it is 0.008. Let's run this cell to find the index. Here we are able to find the point, and now here we will be able to locate the position. So this is the position. You can see this is the position of the point. So we have located more than 1 points with the probability of 0.008. Why we have 3 points? Because there are more than 1 point, or there are exactly 3 points which has the probability of 0.008 either with cluster 1, either with cluster 2, or with cluster 3. So we can scroll up and we can find these points. We have just find 1 point, 0.008, and there will be another point. So you can easily find this is another point whose probability with some other cluster is also 0.008. So in this way, you can find the points by putting the probability in the equation which I provided you. You will get the index, and then you will plot this point. So here are the cluster, and you can see that now we have more than 1 point whose probability with any of the cluster is 0.008. So in this lecture, we learn how to implement GMM clustering with Python. We also learn what are the limitations of k-means clustering. We observe those limitations, we address those limitations using GMM clustering. We saw that how to calculate the probabilities with GMM clustering, how GMM clustering assign different membership in terms of probabilities to different data sample. We also learn that we can easily find any point on the cluster whose probability or whose membership is with more than 1 cluster. We take more than 1 example. Similarly, student, you can put any probability value and you can find the point, or you can locate the point in the cluster. So the last example we saw is that we select the probability value of 0.008, and we saw we have 3 points which are indicated here with the brown color whose probability is 0.008 with more than 1 cluster. So in this way, in this lecture, we learn how to implement HMM clustering, why it is a soft clustering or a membership clustering. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are once again implementing GMM clustering in Python. So this is our project 2 of GMM clustering. So here I am at project 2 of GMM clustering. Click on this file so that we can open it in our Google Colab environment. So here we are in our project 2. So what we are going to implement in this project. So basically we are going to see 3 important things as we did in project 1. First, we will implement k-means clustering. Then we will see the limitations of the k-means clustering. And then we will see how GMM clustering will address the shortcomings or the limitations of k-means clustering. So the first step is to import all the necessary Python libraries. So I need NumPy, Matplotlib, and Pandas. Let's run this cell to import the libraries. Now it's time to create the data. Here I am creating the data using np.random.randn command. So if you remember, I have been used this data many times before this section. That is, in the section of k-means clustering, we use this data and we learn how to create this data. And also in the section of hierarchical clustering, we create the same data. Now, let's see how we have created these data before and how we are creating this data now. So here, the first step is to create 6 different data sets from small x1 to x6. So these are small or with the small letters x1, x2, x3, x4, x5, and x6. In all these 6 datasets, I am using np.random.readn, and I am adding a constant value so that every time when I run this cell, I will get 6 different values each time of each dataset. The size of each data is 100 by 1. Let's run this cell to create these 6 datasets. The next step is to horizontally stack these datasets to transform these 6 into 3 datasets. So I am horizontally stacking x1 and x2 to get x1. Then I am stacking x3 and x4 to get x2, and I am stacking x5 and x6 to get x3. Let's run this cell. Now we can see the shape of x1 here. If I scroll down, I can see the shape. You can see now the shape is 100 by 2. Previously, when I have 6 data sets, the shape was 100 by 1. Now with horizontal stacking, the shape of each x1, x2, and x3 is 100 by 2. Now it's time to create the final form of the data. The final form of the data is to get the vertical stacking of x1, x2, and x3. When I will do the vertical stacking of these 3 datasets, I will get the final form of my data. Let's run this cell to create the final form, and now the shape is 300 by 2. So the shape of x1, x2, and x3, shape of each these x1, x2, and x3 is 100 by 2, and the final shape is 300 by 2. Now it's time to plot k-means cluster. And we know that the first step is to get the optimal number of clusters using elbow method. So this is the same way of creating the elbow curve, which we have learned in our k-means section. Let's run this cell and see the elbow curve. Now this is our elbow curve. If we see the elbow curve, we can see that at number of cluster equals to 3, we have a significant change in WCSS value, which is within cluster sum of square. So before this 3, there is a rapid or significant change or significant decrease in the value of WCSS. And after number of cluster is equals to 3, this line becomes almost flat. So here is the point where we select the number of cluster. So for this particular project, according to elbow method, we are going to select number of cluster equals to 3. So here we have selected 3 cluster. Here I am importing k-means. Here I am generating k-means function by inputting number of cluster is equals to 3. K-means plus plus is the algorithm, and in it is auto. And we know that this code or this function is used to create the random location of the centroids. So let's run this cell to create the predictions for k-mean. And here are the predictions, and we can see that we have 3 kind of prediction. 2 indicate cluster number 3, 0 indicate cluster number 1, and 1 indicate cluster number 2. So we have 3 clusters for k-mean. Here is the time to create the centers or to see the centers of the k-mean clustering. And now it's time to visualize the cluster. Now we can see that here is the cluster, and if we see this, there are 3 clusters. We have divided into 3 clusters. Here we can see that the clusters are overlapping. This is cluster 3 and this is cluster 1. Now here the clusters are overlapping, and if we see, there is no point in the overlapping region. In the project 1, we saw that there were a few points which were in the overlapping region of more than 1 cluster. So here we did not get any point which is at the overlap of the cluster. Now what we can see that the clusters are overlapping. Here is the percentage of overlap, but in the overlap region, there is no point. So what we can do, we can run this data again. So this is the advantage of creating a random data. So here we are creating a random data. Every time we run this cell, we will get different form of data. Let's see, let's run this data again. We might get the points which are at the border of two cluster or which may have the membership of more than one cluster. So this is the advantage of creating a random data or simulating your own data. So every time you run this cell, you will get a new data set. So this is also a very good example or very good way of practicing more and more. You do not need to import some external data every time. You just need to run this cell every time, and every time you will get a new set of data samples. Let's run this cell. Let's run this cell again, and we run this cell. We create the elbow method again, and we will see again we have number of cluster is equals to 3. Create k-means clustering. Here is the k-mean clustering. This is our Y predictions, and we again see that we have 3 kind of clusters, and these are the center of the cluster, and here we are going to visualize the clusters. Now this time we can see that there are 3 points. There are 3 points which are at the border of 2 cluster or which may have the membership of more than one cluster. So you can see that if I run this code again for the data creation, I will get the new data points and I will get the new form of the cluster. So this is the advantage. You can create as many data set as you want, and you can practice more and more. Now we have these 3 points, especially this blue point, which is at the border of the 2 cluster. This is basically inside this cluster. And if we see that this is the intersection or the overlapping region. So all these 3 blue points should have the membership of these 2 clusters, which are cluster 1 and cluster 2. Now, the problem with k-means clustering is, or the shortcoming or the limitation of k-means clustering is that it is a hard clustering. It will not tell you about the membership of a data sample with more than one cluster. So what k-means clustering is doing here, that it is assigning the blue cluster to these 3 points, which may have more than, which may have the membership of more than one cluster. So we will address this shortcoming or the limitation of k-means clustering with the help of GMM clustering. So here is the time to apply Gaussian mixture model clustering. So the first step is that I am importing Gaussian mixture from sklearn.mixture. Here I am inputting number of components is equals to 3. So basically the number of components is equals to the number of clusters. Here I am getting the predictions. Let's run this cell. Let's see the predictions. So again, we see that we have 3 kind of values or indices in our predictions. 0 indicate cluster 1, 2 indicate cluster 3, and 1 indicate cluster 2. Let's visualize this. So we can see that this is the cluster. These are the cluster, the 3 clusters which are found by GMM clustering. So the major advantage of GMM clustering, we know from our previous lecture of this section, is that it will give you the membership of those points, especially which are at the border of 2 points or at the overlapping region of the 2 clusters. So let's get the prediction probabilities of each data point. These are the probabilities. Now in the probabilities, we need to find those points which we saw and which may have the membership of more than one cluster. So this might take some time in order to see the probability. So we have 99.8 with cluster 1 and 0.002 probability with cluster 3. Let's see some other values. So these 4 data sample also has the membership of more than one clusters. Here it is 88.1 and 11.9. So we can select this point. So this point has 88% probability of being a part of cluster 1 and 11.9% probability of being part of cluster 3. If we scroll down, there are many points, but this point has high probability. Maybe we need to select this point. This is much better point. Here we can see that the probabilities are very decent values. Probabilities have very decent values with both cluster 1 and cluster 3. So this data sample has 68.3% probability of being with cluster 1 and 31.7 probability of being with cluster 3. So let's find this point in cluster which has the probability with cluster 1 of 68.3. So I will put 0.683 in my equation here. 0.683 6, 8, 3. So we remember this equation from project 1. This equation will help us to find the index of that point, and then we will find that point by passing the index in our data set. Let's run the cell to find the index, and here is our point, and here we are going to visualize this point. So we can see that this is the point which has a dual membership, and we can see that it is at the border of these two clusters, that is cluster 1 and cluster 2. So this is the same way of finding the point which we learned in project 1 of this section, where we find the point which has a triple membership. So here the point has a dual membership, and we can see that we have successfully find the point by observing the probability of the point from the list of the probabilities. So in this lecture, we learn how to implement k-means clustering, how to find the point or more than one points which should have the membership of more than one cluster. K-mean clustering does not address this problem because it is a hard clustering. So we solve this problem with the help of a soft clustering technique, which is GMM clustering. So with the help of GMM clustering, we find the probabilities of those points which has the membership of more than one cluster. So if you run the whole code again, you will get new points because we have created the data using np.random command. Every time you run this file, you will get a new data set, you will get the new position of the points, you will get the new points at the border of different cluster. So you can run this whole file again and again, and you will see the difference, you will get the experience, and you will learn a lot. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So we are here at project 3 of GMM clustering. Let's click on this file so that we can open it in our Google Colab environment. So here we are at our project 3, and in order to solve this project, I need NumPy, Matplotlib, and Pandas. Let's run this cell to import these important Python libraries. Now, the first step is that we are creating data using sklearn, and we are using a function makeblobs. You have seen this function many times now in this course. You have seen this function in k-means clustering as well, in hierarchical clustering as well. Now, again, we are using this function to create our data set. So the input to this function makeBlob is number of samples. So the number of sample we are using is 200. Number of features are 2. And here we are passing a random state equals to 42, so that whenever we run this line of code, we get same data samples. So we are importing this from sklearn. Here we are creating a data, and here we are extracting the features from the data. We know that the data is in the form of features and labels, so we do not need labels for the clustering assignment. Therefore, we are extracting only the features from this data. So here we are observing the data. So this is our data. We can see that it has a 3 form of clusters here. So this is the shape of the data which we obtained from a function known as makeBlob. Now, what I am going to do, I am creating another data, and this is a very small data. I am calling it data2, and it is just 2 by 2 matrix. Let's see how it looks like. Let's run this cell, and let's add one more cell and pass data2. Let's run this cell to see the data, and we can see that this is just a 2 by 2 matrix which is created using NumPy array. So this is my second data, and this is my first data which I created with makeblobs. Now what I am going to do, basically I am taking the dot product of these two data, the data which was created using a function makeblob, and this is a simple 2 by 2 matrix data. What will happen if I take the dot product of these two data? Let's see. Let's run this cell. See the shape. The shape is again 200 by 2. Let's see the data now. So this is a stretch data. What I have done is basically I have stretched this data. I have stretched this data or these clusters, and I have stretched this cluster. Now these three clusters after stretching looks like that they have 2 clusters, but now they are still 3 clusters. This is cluster 1, and this is cluster 2. Here you can see this is a separation. So basically I have created the overlapping cluster. since I want to see the limitations or the shortcoming of k-means clustering, and I also want to see how GMM clustering solves the limitations or how to address the shortcomings of k-means clustering. So I have created the data which is overlapping. I have created the data where the clusters may be overlapping. So let's see how they look like. First, create an elbow curve to find the optimal number of cluster. So let's run this cell. And we can see that this is our elbow method. Now, according to this elbow, we can see there are two important points at cluster 2 and at cluster 3. After cluster 3, we can see the flat line. There is no change in sum of square values. Almost it is a flat line after n is equals to 3. After n is equals to 2, there is n is equals to 2, there is still a significant drop in the value of sum of square, but after n is equals to 3, we cannot see this significant drop. So here we are going to take number of cluster is equals to 3. Now it's time to apply k-means clustering and see these clusters. So here I am generating a k-means function, and here I am fitting to get the predictions from my data. And here are the predictions. And we can see that we have three kind of cluster. 2 represent cluster 3, 0 represent cluster 1, and 1 represent cluster 2. Now it's time to calculate the centers or the centroids of the k-mean cluster. And here is the visualization of the cluster. So this is the same code which you have seen many times in k-means clustering, the hierarchical clustering, and now in GMM clustering in project 1 of the GMM clustering and in project 2 of the GMM clustering. So here we are visualizing the cluster. Now we can see that we have three clusters. Now this cluster is separated very well. Here we have the overlapping cluster, and we can see that we have cluster 1 and cluster 3, which are overlapping, and in the overlapping region, we have few data points. But the problem with k-mean clustering is that k-mean clustering is not telling anything about these data points which are at the border of two clusters or at the overlapping region of two clusters. So k-mean clustering is not assigning any membership to those points. It is hard clustering, and it is assigning only one cluster even to those points which are at the overlapping region, especially this red point and this green point. Now it's time to implement GMM clustering so that we can address this shortcoming of k-mean clustering. So here we are applying a Gaussian mixture model clustering. I am importing Gaussian mixture from sklearn.mixture. This is the function, and there is only one input, that is number of component is equals to 3, which is equals to the number of cluster which we get from the elbow method. So let's run this cell to get the predictions for GMM clustering. And here we can observe the predictions, and we can see that we have three kind of predictions. That is, we have 2 which is representing cluster 3, we have 1 which represent cluster 2, and which we have 0 index which represent cluster 1. Now plot GMM clustering. So if we plot GMM clustering, we can see that we have the overlapping points. Now it's time to calculate the probabilities of these points so that we can identify that these points have membership of more than one cluster. So here we are calculating the probabilities, and here is the time to look at the probabilities. Now we can see that since we have 3 clusters, so every data point has 3 probabilities. If we see the first data point, now here the probability is 1. It means this point only belongs to cluster 3, and it has no membership with cluster 1 and cluster 2. Here we can see that this cluster has a very small membership with the cluster 3. This point has a very small membership with cluster 3 as well, and it is actually a part of cluster 2. So let's scroll down and find a point which has some highest value of the probabilities with more than one cluster. So this is the first point. We can see that here this data sample has 43.4% chance of being a part of cluster 1 and 56.6% chance of being a part of cluster 3. And here if we see, this is 43.4, and here is another point which has 40.7 and 59.3 membership probabilities. Here there is another point which with high probabilities value. So it is 44.6 likely to be a part of cluster 1 and it has a probability of 55.4% to be a part of cluster 3. So what we are going to do is we are going to select this point whose probability is 0.446 or 44.6 with cluster 2 and 0.554 or 55.4 with cluster 3. So let's find this point on our clusters, 0.446. Let's put this value 0.446 in our equation in order to find the value. So the value is 0.446 here. And let's run this cell to find the index of the point. And here we are passing the index to get the point. And we can see that these are the coordinates of a point. Okay, now it's time to plot this point on the clusters and observe this point. So we can see that here is the point which has the 44.7% probability of being with cluster 2 and 55 point something probability with cluster 3. So in this way, we can see that GMM clustering is addressing the shortcoming of k-means clustering. So k-means clustering is a hard clustering and GMM clustering is a soft clustering which assign memberships to every point, and it is more important for those points which are at the borders of two clusters or at the overlapping region of the two clusters. So in this lecture, we learn how to implement k-means clustering, how to find the shortcomings or the limitations of k-means clustering, and how to address the limitations of k-means clustering with the help of GMM clustering. We successfully find the point which has a dual membership, and we successfully find that point in our cluster as well. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to learn a binomial distribution. Now we are going to learn this distribution because we have to learn the expectation maximization algorithm, which is also known as EM algorithm. So EM algorithm is very important part of Gaussian mixture model clustering. And during the learning of EM algorithm, we need the concept of binomial distribution. That's why first we want to learn the binomial distribution. So what is binomial distribution? So experiments in binomial distribution consist of repetitions trials with each with two possible outcomes, that is success or failure. So the application of binomial distribution is for those experiments where we have two possible outcomes, that is success or failure. Suppose we flip a coin and we want head. It means head is our success, and if we do not get head, that is our failure. Similarly, we can also apply the concept of success or failure in rolling a die. If we roll a die and we want even number, so even numbers are 2, 4, and 6, and we know that die has a 6 sides. So if we roll a die and if we get an even number, any of the even numbers, it means that is our success, and if we do not get the even number, that is our failure. So those experiments where there are two possible outcomes, that is success or failure, we can use binomial distribution to find the probability of the event. So this is the equation of binomial distribution to find the probability of the events. Here there are a few parameters n, k, p, and q. So we can see that this equation is start with the combination of n and k. This is the n combination k, where n is number of trials. So if I repeat the trials 10 times, if I flip a coin 10 times, then the number of trials are equals to 10. Similarly, if I'm using a die for my experiment and I roll a die 5 times, then number of tries or number of times I roll a die will be denoted by n. K is the number of successful trial. So out of n, how many times my trial is a success? So the concept is that if I flip a coin 10 times and I get only 3 heads, so n is 10, which is number of trial, and the successful trials are only 3, that is I get a head only 3 times. So k is equals to number of successful trials. P is the probability of success and q is the probability of failure. If a coin is a fair coin, then the probability of success, that is getting head, is also 0.5, and the probability of a failure is also 0.5. And similarly, if a die is fair, then the probability of getting even and getting odd number or not getting an even number is also same. So this is the equation which we will use to find the probability of event using binomial distribution, especially those experiments where we have two possible outcomes, that is success and the failure. And this is the way of finding the combination of n and k, and the equation is n factorial over k factorial and the difference of these two, that is n and k. So this is the equation which we will use to find or to calculate the probability of the events if our experiments fall in the category of binomial distribution. That is, we have two possible outcomes for our experiment, either we success or we fail. So here is the numerical example. Suppose we have a biased coin where the probability of getting head is 0.6. And if the experiment is performed 5 times, what is the probability of getting 3 heads? So we can see that here the probability of getting head is 0.6. So this is the probability of success, that is P. So here you can see that I have put P equals to 0.6. Now, what is the probability of failure Q? It is 1 minus P, that is 1 minus 0.6 is equals to 0.4. We are repeating the experiment 5 times. So our N is 5 and we are getting head only 3 times. So our successful trials are equals to 3. So out of 5 trials, we have 3 successful trials. So this is 5, this is 3, this is 0.6 and this is 0.4. So I hope you understood this. This is very easy to understand. Now it's time to solve. So how to solve 5 combination 3? So if we go back, we can see this is the equation. That is, if n is equals to 5, k is equals to 3, it is 5 factorial, 3 factorial, and 5 minus 3 factorial. So the 5 factorial, 3 factorial, and 5 minus 3 factorial, which is 2. So these are the value of P, and this is the value of Q. So in order to solve 5 factorial, so 5 factorial is basically 5 times 4 times 3 times 2 times 1. And if we stop before reaching to the final value, we can stop with the help of factorial sign as well. So 5 times 4 times 3 factorial divided by 3 factorial over 2. So 3 factorial is 3 and 2 factorial is 2 times 1, which is also equals to 2. So in this way, what will happen? This 3 factorial will cancel out with this factorial. This 4 will cancel out by this 2. So we are left with 5 times 2, which is 10. So if I solve this combination of 5 combination 3, I will get the value of 10. I will get 0.216 from here and 0.16 from here. And the final probability is 0.35. It means what this probability is explaining. It means if I perform the experiment 5 times, that is, if I flip a coin, which is a biased coin 5 times, so the probability of getting 3 head is 0.35. So in this lecture, we learn the basic concept of a binomial distribution. We see where binomial distribution is applicable. We see the binomial distribution is applicable only to those experiments whose outcome is either failure or a success. Then we solved a numerical example on the binomial distribution, and we find the probability of getting 3 heads if the experiment is performed 5 times. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. In this lecture, we will learn expectation maximization algorithm, or in short, EM algorithm. So what EM algorithm does for us and what is the problem which it solves? So suppose we have a data set with D features and the data samples come from K Gaussian distribution, each having a different mean and variance. Since we have K different distribution, therefore we expect K cluster. Now the question is how to determine mean and variance of these distribution. So the solution is that we determine these values using algorithm known as expectation maximization, or EM algorithm. So basically this EM algorithm is used in GMM clustering to update the value of mean and variance. We know that in K-mean clustering, we need to update the centroid of the cluster, but in GMM clustering, we need to update the mean and the variance of the cluster. And we also know that if data comes from K different distributions, then we expect K cluster. So every time we need to update the mean and variance of the cluster so that we can assign a correct cluster to the data point. So for updation of the mean and variance, we use EM algorithm. So EM algorithm is algorithm for finding model parameters. EM is also useful when the data has missing values or variables called latent or hidden or unknown variables. So when we apply expectation maximization or EM algorithm to GMM clustering, then it is used to find the model parameters mean and variance. That is to update the mean and variance of the cluster. However, EM can also be used in other applications. Suppose the data has some missing values, so we can use the available data to find those missing values. So those missing values are also called latent values, hidden values, or unknown variables. So how EM works? So EM use existing data to estimate the values of unknown variables and then find the model parameters. So it has two steps, the expectation step and maximization step. That's why it is known as expectation maximization algorithm. So what we do in expectation step? So in expectation step, we use the given data to estimate the unknown data or the missing data. And when those missing values are found, then in the maximization step, we use the complete data to update or optimize the parameter. So this optimization is based on the estimated values generated in the expectation step. So in the expectation step, we find the required value or the unknown value or the missing value. When those values are found out, after that, in maximization step, we use the complete data, that is the available data and the missing data, which is now has been found out, to optimize the parameter or to update the parameter. So that is done in maximization step. So let's understand more about the expectation step of EM algorithm. Suppose we have a data with n number of samples and we want to divide that data into k cluster, that is from C1 to Ck. So we know that in GMM clustering, we need to find the membership or the probability with which every data sample belong to a particular cluster. So if we want to find the probability of a particular data sample Xi belongs to a particular cluster Ci, in that case, this will be the equation. The probability of Xi belongs to Ci will be the probability of Xi belongs to Ci, sum of the probability that Xi belongs to all the cluster. Here you can see that this is the probability belongs to all cluster. Now this point is very important, that the probability with Xi belongs to Ci will be high if the point is assigned to the right cluster and low otherwise. So the situation is, if this probability is high, then close to 1. Suppose in the first step that the probability that Xi belongs to Ci is close to 1. Now here is the sum of the probabilities. Then in the denominator, we will also have a 1. That is the probability of Xi belongs to a certain Ci. Then all the other probabilities will be 0 because the sum of the probability should be equal to 1. So if the assigning probability of a cluster to a data point is 1, then its probability with other clusters will be 0. So in that case, we will get the value equals to 1. So in order to get this value, or in order to prove that a correct cluster has been assigned to a data sample, the value of this probability should be high. So this is the expectation part. So basically in expectation, we are calculating the probability that a particular data sample Xi belongs to a particular cluster Ci. Now, when this probability has been found, now it's time to update or optimize this probability. So that will be done in the maximization step. So we find the new probability density function. So this is the equation of finding the new probability density function. And here it is found by the equation number of sample assigned to the cluster over total number of sample. So you know that in both the equation, the denominator is about the total number of points or total number of samples present in the data set. So in this way, we update the parameter based on the values assigned to the distribution. So we calculate the probability in the expectation step, the probability that each data point belongs to a particular cluster. And then in maximization step, we update the probability by finding the new probability density function. So this is the advantage of using expectation and maximization algorithm. And this is the basic algorithm which works behind GMM clustering. So in the next lecture, we will solve a numerical problem on the expectation maximization algorithm so that we can get full insight of this algorithm. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we are going to solve a numerical example on expectation maximization algorithm. So the problem is that we have two biased coins A and B with biased values theta A and theta B. We know that if the coin is fair, then the probability of getting head and tail on the coin is 0.5. But if the coin is biased, then we cannot find or we cannot predict the probabilities without performing the experiments. So here we have two biased coins A and B, and theta A and theta B are the probabilities of getting tails from both coins. So we want to find the probabilities of getting tail from both the coins. And since both the coins are biased, therefore the probability is not equals to 0.5. So we are going to perform the experiments, or we are going to perform the trials with both the coins. So the first step is that we are going to perform two trial with coin A. So in the set of first trial, we have 10 values, or we have 10 events, and out of these 10 events, we have 9 tail and 1 head. In the second, we have 8 head and 8 tails and 2 head. So in total for trials for coin A, we have 17 values for the tail and 3 values for the head. So if we add the value of tails in both trials, we get 17. And similarly, we have 3 heads for coin. So we also perform the trials for coin B. So this time for coin B, we have 2 trials, and we have 5 tails and 5 head in a first trial, and we have 6 tails and 4 head. Rather, we have 1, 2, 3, 4. We have 4 tails and 6 head in the second trial. So if we add the value of tails for coin B, we have 9 tails in total, that is in both the trials, and we have 11 heads in both the trials. So now it's time to calculate these probabilities. Since we have 17 tails for coin A out of 20, the probability is 0.85. Similarly, we have 9 tails out of 20 for coin B, so the probability is 0.45. So in this way, we calculate the probabilities of a biased coin, that is the probability of getting tail from the biased coin, by performing the experiments and creating the set of trials. Now the problem is that if we have a trials without knowing the coin, then how to find theta A and theta B? Now we have only trials, but we don't know which trials belongs to which coin. Then how to find the probability of getting tails from both the coin? So in this way, we have to use EM algorithm. So these are the 4 experiments and trials. We have a first trial, second trial, a third trial, and the fourth trial. And we don't know in advance that which trials belongs to which coin and how to find the probability of getting tail with coin A and coin B. Now the solution is to apply EM algorithm, and we know that EM algorithm has 2 steps, expectation step and maximization step. So in the expectation step, we will start with the first step, that is the expectation step, and this is our first iteration. So we don't know the value of theta A and theta B. But to start with, we set or we assume the initial estimate of these values. So we suppose that theta A is equals to 0.8. This is the estimate value. That is why it is denoted by head. And theta B head is equals to 0.4. So we estimate that the probability of getting tail with coin A is 0.8. And we estimate that we assume the value of estimation that the probability of getting tail with the second coin, which is B, is 0.4. So let's start the expectation step with these estimate values. Now we will have to apply binomial theorem on all 4 trials for both coin A and B. And we know from the previous lectures how to apply binomial theorem. So this is the mathematical equation of the binomial theorem, and we know that we apply binomial theorem when our experiments has two outcomes, that is a success and failure. Now in our experiment, getting tail is a success and getting head is a failure. And here n is the total number of events or trials present, k is the total number of success, p is the probability of success, q is the probability of failure. So we have already studied binomial theorem in this section. Now it's time to apply binomial theorem inside the expectation step of EM algorithm. So the first is that we are applying binomial theorem on the first trial for a coin A. Now, if we see the first trial, we have 5 values of tail, which is our success, and 5 values of head. So therefore, n over k, n is 10, which is total number of experiments. 5 is k, which is successful experiment. 0.8 is the probability of getting tail or the probability of a success. So this is our estimate value. If you remember that our estimate value is 0.8 for coin A and 0.4 for coin B of getting tail, that is the probability of success. So here 0.8 raised to power 5, and then 0.2, which is the value of q raised to power n minus k, which is also 5. So if we solve these values, this become the 10 factorial, this becomes the 5 factorial, and this becomes 10 minus 5 factorial. And the 10 factorial becomes 10, 9, 8, 7, 6, 5, and we can stop here because it will continue till 1. But if we want to stop before, then we have to put a factorial sign again. This 5 factorial is here, and this 5 factorial is 5, 4, 3, 2, 1. Here we are getting the total value of the factorial. So this 5 factorial will be cancelled out by this. And if we multiply all this and divide by this and multiply with these two terms, we will get the probability value of 0.08. So this is the probability for coin A of getting tail from the first trial. Now for coin B, we will repeat the similar. For coin B, again, the estimate values are different. For the coin B, the probability of getting tail, which is successful event, is 0.4, and probability of getting head is 0.5. So if we solve all these values, this is the values obtained from the binomial theorem, we will get the probability of 0.2. Now it's time to normalize these values. So in order to get the normalized values of these probabilities, we will divide the probability of A with the sum of probability A and probability B, and we will get 0.3. Similarly, the normalized value for the first trial for coin B will be the probability of B over probability of A plus probability of B. If we solve this, we will get 0.7. Now we can see that with the normalized value, we will get the sum equals to 1. That is, if I add 0.7 plus 0.3, it is 0.1. And we know that if we have two events, then the sum should be equals to 1. Now it's time to start a second trial. Now this is our second trial, and we can see that here we have 9 tails and 1 head. So for the second trial, the probability of coin A becomes 0.268. This is again, we are using the binomial theorem. We have 10 trials, out of which 9 are successful. That is, we are getting tail 9 times. Then 0.8 is the probability of success and 0.2 is the probability of a failure. So this is the probability of getting tail from coin A during a second trial. And similarly, this is the probability of getting tail from coin B during a second trial. So we keep on repeating this. Now it's time to normalize. When we normalize in the same way which we did for the trial 1, we get the value 0.99 for the second trial of coin A. This 2 indicates the trial and this A is the coin. Similarly, this 2 indicates the trial and this B is the coin, and N stands for the normalized value. So we get the normalized value of coin A and coin B for second trial. Now we will repeat this for trial 3 and trial 4 as well. So for the third trial, the probability which we get from the binomial theorem is 0.0055. Similarly, the probability for coin B of getting tail, which is our successful event, is 0.25, which is obtained by applying binomial theorem. Now normalize these values. So these are the normalized values for a third trial. We can see that this 3 is basically for trial number 3. A is for coin A and B is for coin B. So these are the normalized values, and we can see that if we add those normalized values, we will get 1. So the last and the fourth trial, we have the probabilities of 0.0008 for coin A and 0.215 for coin B. Here we have 3 tails and 7 heads. These are the normalized value for the trial 4 for coin A, and similarly we have normalized value for trial 4 for coin B, and we get the value 0.003 and 0.99. Now, this was the fourth trial, and these are the normalized values. And now it's time to find the total tails and total heads from coin A and coin B using the normalized value in each trial. So if you remember, this 0.3 is the normalized value for coin A after first trial. And in first trial, we have 5 tails and 5 head. So we will multiply this 0.3 with 5 tail, and similarly this 0.3 with 5 head. We will get 1.5 tail and 1.5 head. Similarly, this 0.99 was the normalized value for coin A for the second trial. In second trial, we had 9 tails and 1 head. So we multiply the normalized value with the 9 tail and 1 head, and then we will get 9 tail and 1 head. Here, this is the normalized value for coin A after trial 3. So we multiply this value with the 4 tail and 6 head, because in trial 3 we had 4 tails and 6 head. So we will get 0.08 tails and 0.12 head. This was the normalized value for coin A after trial 4. We will multiply this with 3 tails and 7 head, because we remember that in trial 4 we had 3 tails and 7 head. So if we multiply this with 3 and this 0.003 with 7, we will get these values. Now add all the values of a tail. So total tails are 10.6, and similarly, if we add all the heads here, the total heads, that is 1.51, 0.12 and 0.021, the total heads are 2.6. So these are the total tails and total heads obtained from the 4 trials of the coin A. Similarly, we get the values for coin B for all the 4 trials. So if we add all these values, we will get total tails equals to 10.5 and total heads is equals to 16.5. So these are the values which we have calculated for both coin A and coin B. If you remember, we apply EM algorithm because we only had 4 trials and 2 coins, but we did not know which trials belongs to which coin. Therefore, we were unable to find the probabilities of getting tails directly from the trials. So we apply EM algorithm, and first step was the expectation method or expectation step, where we use all the 4 trials for both the coins. First, we calculate the probabilities of all the trials with the coins, and then we normalize those values. And after getting the normalized values, we are getting now the total heads and total tails for coin A and coin B. Now it's time to maximize these values, or it's time for the second step of EM algorithm, which is the maximization step. So in this step, we will maximize the value, or we will update the value of theta A and theta B. So we have tails on coin A because we want the probability of tail. Tail is our successful event divided by tails on coin A plus heads on coin A. That is the total values of the events. So if we divide those values, we will get 0.8. Similarly, the tails on coin B, we know that the tails on coin B are 10.5. If we divide 10.5 with the tails on coin B plus heads on coin B, we will get the value of 0.4. So in this way, we see that after EM algorithm, we will get the value of theta A, which is 0.8, and theta B, which is 0.4. If we remember, these theta A and theta B are exactly equal to the value which we assume at the start of the algorithm, because we did not know at the start what were the values of theta A and theta B, because we did not know which trials belongs to which coin. So that is the end of the first iteration. And at the end of the first iteration, we see that we have obtained, or we have successfully obtained, the assume value. If we are not able to find the assume value after iteration 1, then we have to go to the iteration 2, or we keep on going to the iterations until we reach to our assume values. Suppose if this value were 0.7 and this value were 0.5, then we will start second iteration by assuming that these are now the estimate value, and then we continue to repeat our experiment for coin A. For coin B, we keep on calculating the normalized value, then we keep on calculating the total head and tail on these coins, and then we maximize those values in step 2 of EM algorithm. So we keep on repeating until we reach our estimate value. But luckily here, we reach our estimate value only after iteration 1. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture.